Hi there, Year 12. I thought I might just run through this section on kinematics on video because I may not be here. I'm not sure where I'll be on Wednesday. Anyway, so in 19C1 and 2, basically we're applying all your calculus to movement or the kinematics. So we start off with just a simple example where we're looking at a car travelling at a constant speed of 50 kilometres per hour. And remember, we're only looking at things that are moving in one dimension, in a line, not going in two dimensions like projectile motion that a lot of you would have done, or some of you would have done in physics. So, car travelling at a constant speed of 50 kilometres per hour, you probably remember from middle school that if in 2 hours, how far does it travel? So you'd be going like the distance travelled is going to be 50 times 2, which is 100. What are our units? Kilometres, because we're kilometres per hour. If we wanted to graph that, our velocity function in this case is 50. So we would graph it and we'd have a nice straight line at 50. And if we want to say after 2 hours, so here's our 2, then we can see that when we go 50 times 2, we're effectively finding the area under the curve. And now when we think area under the curve, we're thinking integration. So when we integrate velocity, we're coming up with distance. So, do we know where the car was at the beginning? We know it's travelling at 2 hours, but there's no information here about where it started. So if I wanted to integrate, so I'm sort of running two columns here with the storyline and then what we do with our graph and everything. So in terms of distance in relationship to time, how far it's travelled, we want the integral of our velocity function. So we can see that's the area under the curve. So in this case, we want the integral of 50 dt, because t, time, is our variable. And we would have it from certain times, but at the moment, let's just work with this. So integrate that with respect to time, we get 50t plus c. And because we don't know any conditions about it, we don't know what to do with the c. So we know that our line, let's say, is starting at the origin. The gradient of this line is 50, because that's in our y equals mx plus b. That's like our gradient, that's the slope of our displacement line. So this has a gradient of 50 kilometres per hour, but it could just as well be up here. That's another option for our displacement. Because, as I said, we don't know where it started. So it could be anywhere up and down that curve, but we know the gradient is 50. So our gradient is 50 kilometres per hour, but don't have any initial conditions. If we want to actually get the displacement, then we just use our definite integral and we use T1 and T2. We can substitute those times in to find the exact displacement during that time. So that's a nice simple example. Let's step it up, and in this case, we've now got a car that the velocity is not constant. So the velocity function, 8t plus 40, is saying that the velocity is changing over time. How fast is it going at the beginning when t is equal to 0? We can substitute in. V of 0 is 8 times 0 plus 40. So the initial velocity is 40. Let's assume we're talking kilometres per hour. Okay. So how fast is it going after 3 hours? We want the velocity after 3 hours. We're going 8 times 3 plus 40. 3, that's 24. 64 kilometres per hour. So it's getting faster. So here we are initially at 40, and at time 3, we're now at 64. All right. So our velocity function, 8t plus 40. So how far did it travel in 3 hours? So again, we want to think about area under the curve. So that's our area here. The dots always line up. So that's how far it's travelled. Now that we've done some calculus, we can see that's the area under the curve. Whereas if you think back to year 10, if you wanted to get how far it travelled in 3 hours, you'd think, well, what is its average velocity? Because we talked about displacement as the average velocity times time. What is the average velocity? Average velocity is your initial, which was 40, plus your final, and over 2, because we want to just get the average. So that gives 104. Our average velocity is 52 kilometres per hour. So now to get our displacement, just coming down here, we can go 52 times 3 is 156 kilometres, just using an average velocity. Or we can do our area under the curve, and we can calculate that area, and basically, because it's a nice trapezium, you could work out that area geometrically. So the displacement is your area under the curve. So that's a nice easy one. We've got a nice linear equation for our displacement. And areas can be worked out using geometry. Let's now step it up one bit further. So now we've got an object which has a quadratic equation for its velocity. And if you remember back to when we were doing differentiation and looking at movement, if the velocity is looking like this function, t squared minus 5t plus 4, so I've just done it like this so I can graph it on here. So what's actually happening to our particle? Hopefully you remember, this is our time axis. At time 0, velocity is plus 4. So at this time, at the beginning, what's happening? The particle is moving with a positive velocity of 4, whatever the units are. All right, so let's go, let's put our velocity in meters per second, just to change the units around. So initially, it is moving, and remember, that direction is positive, to the right is positive, to the left is negative. So let's say it's moving to the right at 4 meters per second. All right. What's the next significant point on our graph is this point here at time 1. What's happening at time equal to 1? Hopefully you recognise the velocity is 0. So the velocity equals 0. What does that mean if it's got 0 velocity? It's stopped. Okay. Now, between, here it's stopping again at time equal to 4. What's happening in this region here, between 1 and 4, it has a negative velocity. At this point, which is our minimum, so between 1 and 2.5, the velocity is negative, is equals less than 0, which means it's moving which direction? To the left. So if it's now moving left, up here when t equals 1, it stopped, it must mean it turned around. So it stopped, turned around and started going left, negative velocity. What happens at 2.5? That's a maximum, or I'm sorry, a minimum velocity. So it's the smallest amount of velocity. In other words, it's got the maximum speed in the negative direction. So at t, this is 2, 3, in that region, it's going fastest at time equal to 2.5. All right, what's happening now at time equal to 4? T equal to 4, it is now, velocity is 0. In other words, it's stopped, and it's now moving from a negative velocity to a positive velocity. So it's now, when we say here it stopped, so that means if it's going from negative velocity, it's going in a negative direction to a positive direction. So it stopped, turned around, and now moving to the right. Bit more space. All right, so now what's happening in the last section up here, between time 4 and 6, the velocity is positive, so it's moving in the right direction. And it looks like at time 6 it's got a velocity about 10. So, if you're not sure about that, stop it and replay that. Motion diagram. What's the particle doing? Remember we said initially it was moving in the positive direction, starting at t equals 0. It was moving in the positive direction, it stopped, turned around, turned around and went back that way. So this turning around happened at t equal to 1. This turning around happened at t equal to 4, and then kept going. The question is, have I gone far enough in this direction to the left? Does that match what's the graph's telling us? So we need to do some calculation. I'm guessing I'm a bit wrong. I probably should have taken it more to the left. But basically, it's heading to the right. Stop, turn around and go to the left. Stop, turn around and go to the right again. How far has it travelled? Remember we talked about in the first 2 examples the area under the graph. So the distance travelled is going to be this area. All right, that's a nice positive direction. But if I want the total distance travelled, then this is a positive, that's okay. That's how far it's travelled. It's travelled this bit to go back, and it's now travelled this bit to go forward. So they're all distance travelled. So even though this area down here is negative, because it's in the left direction, we want to make that positive. Our first block of time is already positive, and the last part is a positive area. So we can just add those up. We can't do it with geometric shapes because it's a curve. We can't do triangles and rectangles. So we're going to need to do integration. So to get the areas, we need to add up all the areas. So we want the integral from 0 to 1 of our velocity function. And we're going to go minus the the 1 to 4, because in 1 to 4 it has a negative displacement, and we want to make that positive because we want to add up all the distance travelled. And then we add the last one from 4 to 6 of our velocity function dt. Alright, so that's what you could do to get all those different areas. The other option is to take the integral of the absolute value. We talked about that a bit last lesson. So we could say for the distance travelled is equal to the integral from 0 to 6 of the absolute value of the velocity function dt. So if we graph what that would look like, and I haven't got the exact graph, just pull this up a little bit higher. All right, but we know here's 1, 2, 3, 4, 5, 6. Our curve's going to be coming down here, but instead of doing this bit, 2, 3, 4, this bit here, we now go, that's what happens to it for the absolute value of the function. So this is the absolute value of the velocity function. So now when we get the area under that, we're getting all of these, and they all just add up to our boundary of 6. Okay, that gives us all that area. And if you do that in your calculator, using our velocity function, which was t squared minus 5t plus 4, integral 0 to 6, t squared minus 5t plus 4 brackets. Oh, I don't need that because I'm doing absolute value. Acts like a bracket. dt. Put that into your calculator, and you come out with, comes out about 15 if we're doing meters and meters per second. Does that answer make sense? If we think about it, can we do that? I need to look at another graph so we can make sense from another graph. So here I've got the velocity function graphed. Okay, I then have done the displacement graph. Okay, and our displacement is going to be the integral of our velocity graph. So if we integrate this function, then we go to the integral of t squared minus 5t plus 4 dt equals t cubed over 3 minus 5t squared over 2 plus 4t plus c. If we assume that initially the particle was at 0, then that's our displacement function without the c. So, doing that, so I'll graph that up. That's the velocity function up here that we've already looked at, this top one. All right, so underneath here I've now put the displacement function. And if we think what this is saying, at time 1, which is where we saw it turn around, it had gone about, let's see, that's about 2 units. Then it turns around and comes back, so it's sort of gone up 2 units. Remember our motion graph? So we've got our particle, it's going about 2 units to the right, then it stops and turns around and goes about another 2 units, this is approximately, 2 units back, that takes us to this point. It now goes back past where it started, that's like the origin, 0 displacement. So this is time, and this is displacement, yes. This is displacement, remember, not speed. So it's now back going past the origin where it started. It now comes down to, oh, what's that, 2.5-ish. You need to get exact values. So it keeps going this way, another 2.5. Now it turns around, does the turnaround, and comes back this distance to the origin again. So we're back to the origin and then keeps going. So we've got another about 2.5 here, and where did we finish up? About 6. So this was 2, so we end up about 6 here. So this distance here is about 6 units. So our displacement is 2 plus 2 is 4, 6.5, 8.5, 9, 6. So our total distance is approximately 15, because we've just added 2 plus 2 plus 2.5 plus 2.5 plus 6. And that's where we've ended up at times 6 times 0 times 1 when we did the turnaround, times 4 when we did the turnaround. Here's your origin. All right. So we can talk about the distance travelled as the area under the graph, or from a displacement graph, we can work out how far it's gone in the right and the left direction. Obviously, the total displacement from when it started, here it started at 0, and at the end it ended up 6 units to the right. So that's the displacement, the overall change in position. But in terms of distance travelled, it's gone, the particle's gone a long way. So we're going to leave it there, and I might get around to doing the other video, but at least that's a start for 19C.1. So thanks for listening. Don't forget to stop and take notes where you need to, and come with your questions. Thanks. Have a good evening.